Hi, everybody. So the next topic we're going to cover is global climate change. And I saved this one for last because it is the longest topic. And the reason am going to spend a decent amount of time on climate change is because I want to make sure that you understand it thoroughly. It's one of the things that shows up in the news the most, and it's also rather controversial in the American public's view, but among scientists, it's actually not very controversial at all. There's controversy about what we should do about it, but not so much controversy about the basic science of whether it's occurring or not. So the first thing you need to know with climate change is the difference between climate and weather. And when you listen to arguments from people that deny climate change, often they conflate climate and weather, meaning that they don't make a clear distinction between the two different things. And this is really important, and I will tell you right now, this will be on your exams and quizzes. So what is the difference between climate and weather? Climate is long-term. We're looking at decades, centuries, millennial patterns of temperature and precipitation. So if you look out your window and you notice that it's raining, that's not climate, that is weather. Weather is short-term, local patterns of temperature, precipitation, humidity, and wind. That's why when we want to know what the weather is going to be like outside, we check the weather report or the weather predictions. We don't check the climate report generally. We want to look at long-term climate models if we want to know what the average temperature over the next 10 years will be. That would be a climate prediction. But if we want to know whether we should wear a coat the next couple of days, that's weather. So this used to be my senator, Senator James Inhofe, when I used to live in Oklahoma. And he's famous for being on the floor of the Senate with a snowball and asking, where is climate change? How can we have snow if there's climate change or global warming? And he's confusing climate and weather. You cannot look at whether it's snowing or not today or whether it's unusually cold out today and say that climate change isn't real, because climate is an average over much longer periods of time and regional, continental, or global spatial scales. This is the joke. Here he is with the ham sandwich saying, as this ham sandwich clearly shows, world hunger is a hoax. So the idea is, if I just ate, there must not be world hunger, because I'm thinking about local conditions in a certain time and place and extrapolating them to the whole planet. And that's what some of this controversy has to do with. And as I said, conflating climate and weather. Now, commonly we'll hear, but it's so cold outside today. Now I'm recording this on January 4th, and it's actually in the 60s today, so it doesn't apply so much today. But sometimes we'll have a really cold snap when I'm giving my climate change lectures, and it'll be like 15 degrees outside, and people will be like, what climate change? But climate change is expected to result in increased variability in weather patterns. So just because we have really hot weather or really cold weather is not evidence for climate change. We again have to look at longer term patterns over larger spatial scales. In some places, there have been, on average, cooler winters in North America and Europe over the last 25 years. I'll show you some data later that actually shows that some areas in Louisiana have actually, the winters have been warming. But occasionally we have really cold snaps. And what we're finding is that a warmer Arctic can make the jet stream more unstable and allow more Arctic air to move into the United States. So some places do occasionally get colder. And there's a New York Times article on this here if you'd like to check that out. But this shows an example of the jet stream. It's this barrier of air, and when it moves, it brings cold air with it, or if it goes farther north, then we get more warm air coming in. But very occasionally, this jet stream swoops down into Louisiana, and we get really cold Arctic air, making it all the way down here. And they think that's because a warmer Arctic makes the pattern of the jet stream more unstable. So I want to talk a little bit about what generates climate, and we'll talk about the greenhouse effect before we move into the actual effects of climate change. So the planet has an energy balance. All of our energy comes from the sun, and the sun is very hot, obviously, and that's where our heat comes from. And so that energy comes into our atmosphere. Some of it bounces off and goes back into space, but some of it hits the inside of the atmosphere and is re-radiated back to the Earth. And there are a number of currents and things, air currents, that go along with these processes. How much energy the Earth has and how much is re-radiated back to the Earth from the atmosphere, how much is absorbed, how much is reflected. All of that has to do with the different types of surfaces that we have on the planet. A special term is albedo, which is the reflectivity of surfaces, and how reflective the surfaces on Earth are really affects the temperature. So if something reflects a lot of light, like a mirror, if we had a mirror, it would reflect most of the sun's energy back out into space if it wasn't then trapped by the atmosphere. If we get something that's really dark, so let's say it's really sunny outside and you wear a black sweatshirt, then you're going to be really hot because the sweatshirt is absorbing all of that energy. If you wore a sweatshirt of sequins or like a mirrored surface, almost all of that energy would be reflected away from you and you wouldn't feel hot. So it's how you decide what to wear if it's cold or really hot. So like in the middle of summer, you don't want to absorb all that heat from the sun. So I generally wear a lighter color in the summer, but I'll wear a darker color in the winter. And so we see different surfaces. So like fresh snow has the highest albedo. It reflects a ton of light, not quite as much as a mirror, but it's getting there. And then other surfaces have lower albedo. So like water has a pretty low albedo. Forest, that dark green color, and the browns from the bark has a low albedo. Black soil has a very low albedo. And this is the Earth atmosphere average is about 30. And so you can imagine that if we had less snow or ice, which has a lot of reflectivity, and that gets turned into something darker, then the planet will be absorbing more energy from the sun and it will be hotter. This also relates to the greenhouse effect. So the albedo of the surface of the Earth has to do with how much energy is reflected back. But some of the energy might get trapped and then re-reflected back down to the Earth or re-radiated back down to the Earth by the greenhouse effect. And so this is a greenhouse. The idea is that the sun rays come in, they bounce back off, and some escape back out, but some are re-radiated back down because they're trapped inside the greenhouse. And it has to do with the wavelength. So light has a short wavelength and passes through the glass easily. Some of it's absorbed by surfaces and converted to heat, which has a longer wavelength. The longer wavelength has a harder time passing back through the glass. So the light can pass back out, but a lot of the heat cannot. It is trapped because the longer wavelengths cannot make it back through the glass. It's the same idea with the atmosphere. So the light wavelengths are short wavelengths. They make it through the atmosphere very easily. Some of the heat energy is absorbed by surfaces. Some of it is reflected back. The albedo determines how much is reflected back. The shorter wavelengths can make it back through the atmosphere and back out into space. The longer wavelengths are reflected back down, and heat happens to be those longer wavelengths. And we have a number of greenhouse gases that are good at trapping heat in the atmosphere, and those include carbon dioxide and methane, and we'll talk more about those later on. We find that there is variation in climate around the planet due to uneven heating, and this has to do with the tilt of the Earth. And so different parts of the Earth get more or less radiation at different times of the year. These affect circulation patterns, both air circulation and water circulation. And so we see that there are certain ways that winds tend to move from things like the Hadley cells, Ferrel cells, and polar cells. And there are these regular currents. There is some fluctuation, of course, in them, but we get some basic patterns that also determine our climatic patterns. This shows ocean currents, which are driven by surface winds, and the Coriolis effect, which has to do with the spinning of the Earth. And that also influences climate. So we see the Gulf Stream comes up, and the reason that the UK is so warm in compared to these parts of Canada up here is because the Gulf Stream brings warm water up to the UK, and that gives it a more moderate climate than you would expect for its latitude. Ocean currents act as heat pumps or thermal conveyors, and they move heat from the tropics towards the poles. And these affect lots of different processes and moves heat around in the ocean waters. And that changes the productivity of the ocean, it changes fish migrations, and it can change climate as well. These circulation patterns influence the global temperature patterns. So you can see I said before that the Gulf Current brings this warmer water up to the UK. And so you can see at the same latitude, the water is blue around here, so under 5 degrees Celsius, whereas around the UK, it's closer to the 10 to 15 degrees, which is much, much warmer than we get in these parts of Canada. And so you can see that these currents influence the patterns of temperature in the ocean water.